right, we're going into chapter 22, which is about electrostatics. And I've got this broken into 4 parts. So let's go look at electrostatics. And so we'll look at electric forces, electric charges, and conservation of charge first. So this should be stuff that you already know. At least about electric charges, perhaps. So the idea is that there's a fundamental force, which is called the electric force. And it's related to magnetism, so sometimes it's called the electromagnetic force. And there are basically 4 fundamental forces of nature that are known. And the electromagnetic force, the gravitational force, and what's called the strong force and the weak force are the 4 fundamental forces. So anyway, this is the electromagnetic force is different than gravity in that it can attract and repel, and it has to do with objects that have a charge on them. Now, electric charge is called a fundamental quantity. It's something that you can describe an object by, just like we were describing elements by their density. The charge is one of the fundamental ways we describe particles. So it comes in 2 kinds, of course: positive particles, such as protons; negative, such as electrons. And those 2 charges can, of course, cancel out. So you can have things that are neutral also. Now, a fundamental rule for electricity is that like charges repel and unlike charges attract. So 2 positive charges will repel, or 2 positively charged objects, whereas a negative and a positive will be attracted. So if you've ever done that, charged yourself up on a Van de Graaff generator, what's happening is that the Van de Graaff generator is charged up negatively. When you touch it, you become charged negatively and your hairs become charged negatively. And those hairs are repelling each other, which is why you get hairs flying around there. So one of the demonstrations I have over here is a machine which is kind of like a Van de Graaff generator. It'll charge up, and it's called a Windhurst generator, and it can charge both positively and negatively. So we'll play around with that in a minute. Okay, now usually in an atom, the protons are the positive charges. They are located in the nucleus. The electrons are the negative charges. They are outside of the nucleus. But of course, there are also neutrons, which do not have a total electric charge, and so they don't attract or repel. And those are also located in the nucleus. Now, usually an atom is electrically neutral, which means that the positive and negative charges cancel out. And to do that, you have to have the same number of negative electrons as positive protons. So we've talked about this before. If we had 6 protons in the nucleus, that would make it carbon, and it would also have 6 electrons. And remember, the number of neutrons can vary. We talked about that in chapter 12, I think. Okay, now ions are charged particles because they have either gained an electron or lost an electron. And so that happens a lot. When you become charged as a human, like the girl in the picture there, then she was gaining charges. And so some of her atoms could have been ionized. And of course, if you lose an electron, an atom becomes positive. If they gain an electron, they become negative ions. And we talked about how positive charges and negative charges cancel each other. The proton and the electron can cancel. Well, that implies that they have to have the same amount of charge. And so that was discovered by Millikan in the 1800s. The fundamental charge for an electron or a proton is 1.6 times 10 to the minus 19th coulombs. So coulombs is the unit of charge. So that's a new unit. And for a proton, we give it it's positive. We can just represent it by the letter E because it's used so often in formulas and stuff. So we just call it positive E, and an electron would be negative E. So it's pretty amazing that they have the same charge, even though they are not the same size. So a proton is 200 times the mass of an electron, but they do carry the same charge, except positive and negative. Okay, and so now we're going to go on to Coulomb's law. So I guess rather than, well, I guess it's to stop and start. Okay, so I'm going to stop and then start again.